Hey folks, welcome to my channel Number Pen. So we have the problem on our screen. Let f of x equals 0 for x less than 0, x square for 0 lesser than or equal to x lesser than 2, and for x greater than or equal to 2, we have got it at 4, right? So we've been asked to graph the function and show that the function is continuous in interval, open interval minus infinity to plus infinity, right? So how do we go about this problem? I've just put a rough sketch of x and y axis so that we don't spend too much of time trying to draw this. So I know that to sketch the function, I'll have to consider this in three parts, right? What is my first part? Which is x lesser than 0, which means that my f of x takes a value 0, right? At all points x lesser than 0, right? So what is that? It's nothing but the negative x-axis, right? And what is it? If I pick up a pencil, let me pick up an orange color pencil and do this. I will have to just show all these points lying on the x-axis until I reach x equals 0, right? Because at x equals 0, the function takes x square. And what is my x square at x equals 0? It is nothing but 0 square, which is 0, right? So which means my function, or rather this graph, does not undergo a break at the value x equals 0, because at x less than 0 it takes a value 0, and at x equals 0 we know that f of x equals x square from what we've been given, which is 0 square, which is 0. And then for a value which is infinitesimally larger than 0, which is 0 plus h, right? Which is greater than 0, we still have 0 plus h, the whole square, and h tending to 0. So our function does not undergo a break at x equals 0, though, when we observe f of x, we see that it undergoes a transformation as we move through x, right, from 0 to x square. But at the point 0, our values remain the same. So that is established graphically. So I can comfortably, conclude that the function is continuous at x equals 0. So that is part 1. Now I see that for values greater than 0 and up to 2, not including 2, I have my function taking a parabolic equation x square, right? And how does that equation look? I'm going to draw it. At x equals 1, my function is 1, and x equals 2, my function is 4. So I'm just, marking those points for the sake of, you know, completing this. So we don't have to extend this x square function beyond 2. And why is that? Because this particular function for x greater than or equal to 2 takes a value 4, right? So here again we see that at x equals 2 the function undergoes a transformation, right? And what is this transformation? For values which are very close to 2 from the left, which means x lesser than 2 but very close to 2, we have f of x taking x square, which is nothing but 2 square, which is 4. And if I can call it my left hand limit, and when I work out that number, it will still remain as 2 minus h the whole square, which is h is 0, 2 square, 4 square, 2 square, and 4, right? And for x greater than 2, I still notice that my function takes a value 4, right? And for f of x equal to 2, I have my value which is given to me in the function, which is 4, right? So for all values x greater than or equal to 2, it is 4 is just a straight line which is parallel to the x-axis, right? So this is my 4, this is my x square, and this is my 0, right? So this is my first interval, x lesser than 0. And remember, folks, this extends, right? So I'm not, so this is, a graph is not to scale, right? That's what I mean. And this extends till the open interval infinity, right? And on the left, you have this extending to minus infinity. And on the right, you have this extending to plus infinity, and both open interval, right? So this is how the function looks. And you'll have to believe me, folks, the x square looks like a straight line. It's actually a parabolic curve, sorry. So that's how we draw the graph. And do we really need to work this out, right? And I want you to understand this problem graphically, and that is why we went through the graph in detail. So let me repeat this again. So as x moves through 0 from the left and from the right, we notice that there is no break, right? Because from the left we have 0, which is a constant, and from the right we have x square, and at 0 it takes a value 0 square, which is 0, right? So which means that the graph does not have a break. And it's evident that for all other values x less than 0, the function is continuous because it's just lying on the x-axis, right? And between the point 0 to 2, I'm talking about the open interval 0 to 2, we know that this function takes a value x square, which is a simple polynomial of the degree 2, and we know that these functions are continuous. And we know that it is continuous as well in the open interval 0 to 2. And then finally, I come to the final interval, which is 2 to infinity. We saw that the graph undergoes a transformation as we pass through 2. And approaching 2 from the left hand side, we saw that it takes a value x square, which is 2 minus, and I know what that limit is, right? So my limit extending to 2 but lesser than 2, which is extending to 2 minus, is nothing but my 2 square, which is 4, and then my right hand limit, which is again a constant 4. And both of them are equal, which means the graph does not see a break at the point x equals 2. And indirectly, it means that the graph or the function is continuous at the point x equal to 2 as well. And beyond that, x greater than 2, I don't see a challenge because it is a constant 4, right? Which is a constant function is always continuous, right? So that's how we establish that this particular function is continuous. And I'm not going to show these like the way we have done in our previous problems, right? Write down uh, you know write them down by parts, because in this particular problem we've got three parts, right? One is, I mean, four parts, right? One is your x less than 0, then is your 0 less than or equal to x less than 0 less than x less than 2, which is your part 2, and then your part 3, which is x greater than 2, and then you've got two other critical points, which is probably your part 4 and part 5. Apologies, I mentioned four parts earlier. Probably this problem has five parts, and I've got to examine all these parts, and which we have seen graphically, and concluded that the function is continuous in the open interval minus infinity to plus infinity, right? So I hope you found this content useful. Please do subscribe to my channel and support. Thank you.